Hello everyone. I'm recording this video from California in place of our lecture on Monday. So where we left off on Friday was we were talking about this example of how we do color filtering with PyTorch. And so our goal is to start with color image and basically filter that with 4 different color filters, where this first filter's goal is to produce a heat map of locations in this original image which have the most red, and the second filter's goal is to produce a heat map in this image showing the pixels that have the most green, and so on. So at the end of this, we're going to output 4 different grayscale images, each corresponding to those 4 colors. So how do we do this? So we start with this image. It's a color image. It happens to have 368 vertical pixels, 487 horizontal pixels, and 3 colors. So in NumPy, or skimage, the shape of the tensor is like this. So the color channels are last. So it's vertical horizontal color. But for PyTorch, we need to shift things around. The last 2 dimensions should correspond to these, vertical, horizontal. The first one is how many images are in the batch. We only have 1 image, so that will be 1 image in the batch. And then the next is how many channels, and that's going to be 3. So that's the input tensor, X. And the weight matrix, or weight tensor, which is going to correspond to this operation, it's going to have Cin input channels. Now we know that that's 3 because we have 3 colors in our original image. It's going to have Cout output channels, and we know that's going to be 4. And as a convolutional layer, it has a spatial extent of K1 vertical and K2 horizontal pixels, and for that we're going to choose 9 by 9. So if you can see that here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 pixels each way. And let's remember that a convolutional layer does this operation here at the bottom of the screen. So it takes in this input tensor, and it does a combination of convolution spatially, as well as something like matrix multiplication over the different channels, going from the input channels to the output channels. And another way to say it is, for every unique combination of input and output channel, there is a separate convolutional kernel. That's this one, where you look at all the different K1, K2, and that kernel gets convolved with this input image of that input channel. And once you've convolved all these different kernels n across input channels n, you sum across n. And you do that for every fixed m. And finally, we just have one single bias, scalar bias, for each output channel. So that same bias is used for all the different pixel locations. Okay, so how do we do this in PyTorch? So the first thing we have to do is we have to convert the NumPy image of 368 by 487 by 3 into a PyTorch tensor of the shape that it wants. So we just define a few things. The number of images in our batch is going to be 1. The batch shape, the shape of that tensor for PyTorch, we know it has that that format. These variables, number of channel inputs, number of row, number of columns, were previously set I guess we're not showing that code, but previously set in the code. Now, this next line is where we convert the sizes. So we do this with the transpose operation. So it's sort of a generalization of matrix transpose that works with tensors. And essentially you tell it the order of the different tensor dimensions, how you want them to be read out. So this says go to the original image and first take dimension 2, then dimension 0, then dimension 1. So dimension 2 would be this dimension 0, this one, dimension 1 is that. So as a result of this transpose operation, you're going to get a tensor of this size, 3 by 368 by 47. And then there's one last step, is just to extend this additional ghost dimension here, and you do that by reshaping it to the batch shape. So all that does is adds that extra 1. And now finally we have something of the right shape, and so we just make it a torch tensor, and now we have something we can use with PyTorch. Okay, so next we're going to make our convolutional layer. So we're going to use the conv2d layer. We have to tell it how many input channels, that's 3, how many output channels, that's 4, and the kernel size, that's going to be 9 by 9. So we do this, and we create this model, and what happens is certain weights and weight coefficients and bias coefficients are generated randomly when we instantiated this layer. So then we can go and extract the parameters using the state dictionary by doing model.stateDictionary. And then we can extract from that the weight tensor by doing state dictionary weight, and the bias vector, state dictionary bias, put that in B. And when we print out the shapes, you can see that the shapes are just what we expect. Okay, so now we want to overwrite the weights and the biases with the values we want. Okay, so this is kind of a clever approach here that uses PyTorch broadcasting. So actually, NumPy broadcasting. So we're going to think about the color processing and the spatial processing, the convolution, separately. And that is because in the special way that we're creating these, you can see that spatially they all look the same. They're all a Gaussian kernel. The only thing that's different is the color of each one. So, so what we can do is we can make this matrix as a color weight matrix where each of these rows shows the red, green, blue values of the 4 filters. So this is, the top one is filter number 1, the next one is filter number 2, and so on. Number 3, number 4. So when you look at filter number 1, these are the weights. So we're going to assign a 1 to the red weight and minus 1/2 to the green and blue weights. So another option would have been to set these at 0. That would have worked fine too. The results have been slightly different. But by making these numbers negative, we're actually giving like a negative weight to anything that has green or blue in it. So this is how we created that first filter. The second filter, you can see we have a 1 weight for green and negative weights for red and blue. The third filter, we have a 1 for blue and negative weights for red and green. And this last one, we have positive 0.5 weights for red and blue, and then a negative 1 for green. So that's how we got these colors here. Okay, and so that's, you could say, purely spatial processing purely color processing. So if I had just a single pixel, single color pixel, and I wanted to do this filtering, this matrix would be enough. Essentially, you could multiply this matrix times a 3x1 vector of red, green, blue in that single pixel, and you would get a 4x1 vector, which would have essentially, the strengths of that first, second, third, and fourth filter within those colors within that original pixel. Okay, so that's what we would do if we had a single pixel, but we have many pixels and we want to use a Gaussian kernel in the pixel domain. So we already saw how to do this in a previous slide. We can use this Gauss kernel. We just tell it the number of rows and columns, and then this is the sigma, the width, how quickly the Gaussian decays. So this is the purely spatial aspect of the filter, and then this is the purely color aspect of the filtering. And then finally, we are going to merge those two in this command down here to get a four-way tensor. So we're going to use PyTorch broadcasting, which is something we've seen before in different lectures and labs. So this is a two-dimensional matrix. This is a two-dimensional matrix. So let's expand the spatial matrix G into a four-way tensor where the last two places in the tensor, last two dimensions, will be the vertical and horizontal, and then the first two are these sort of empty ones. And then for this color weight matrix, let's make that a four-way tensor where the first two are the color channels, and then these last two are empty. And when we do this multiplication, NumPy knows how to do this, and it basically makes a four-way tensor that in terms of the color processing does this, and in terms of the spatial filtering does this. For the bias vector, we just set that to zeros. We don't want it to do anything. And now that we have these weights and biases, these are in NumPy, we convert them to torch tensors. We overwrite the state dictionary elements, and then we load the state dictionary back into the model. And now that the model's all set up, processing the data is pretty trivial. You just do model applied to xtorch. Xtorch was our original color image to get ytorch. And then finally we have to detach it to NumPy in order to print it out, to plot it. So this is what we have. Remember, we expect to get 4 output channels. Each is going to be the size of this original image. And you can see that the first channel, this is a heat map where the brighter pixels correspond to there being more of this color in the image. And you can see that this orange has the most of that color, and that's why it's the lightest here. In terms of green, you can see that the apples, they have the most green, and so they show up brightest in this heat map. For blue, those would be these two apples, especially the one on the right, and then this pinkish purplish color, the most energy would be those orange and apple on the right. So you can see the effect of color filtering and understand the notion of having more than 3 channels. As a human, we can't really view these all together. We can only see things in 3 colors. But there are many animals out there that can see more than 3 colors, and it's just a particular limitation that we humans have. All right, so so these kinds of things are what we find in the middle of deep networks like AlexNet and so on, although we tend to see many more than 4 channels. So in particular for AlexNet, in the first layer, we've gone from color image of 3 channels to these feature maps, 55 by 55 pixels of 96 channels. And one way to visualize the convolutional kernels that took us from the first layer to the second layer, we know that they're 11 by 11. And we could, so in total, we have 3 times 96 grayscale filters, but we can actually merge, for each one of these 96, we can merge these 3 together using red, green, and blue and plot them as a color kernel. So that way we're going to have 96 color kernels, red, green, blue, color kernels of size 11 by 11. And that's what's plotted here. And I want to emphasize that these are not things that we have made up. These are things that were learned using the ImageNet data set for the purpose of eventually classifying among 1,000 classes. But these are the kernels that it found most useful for that learning task in the first layer. And when you look at them, you can see they're very much like little edge detectors, similar to little Sobel filters that have a plus and minus with sort of a Gaussian shape. Some of them are, you could say, maybe double edge detectors and so on, and they have different orientations, different angles. Some are horizontal, some are vertical, and so on. A lot of them look mainly black and white, which is interesting. In other words, there's equal amounts of red, green, and blue in the 3 different kernels that we plotted together as a color image. However, there are cases here where you see that it is colored, green and purple and so on, blue and purple. So it's very interesting what it learned. There's checkerboard patterns, but these are the most basic building blocks that it can put together to eventually classify very complicated shapes of 1,000 real-world channels. All right. Okay, so that's AlexNet. So we're going to move on to a bunch of different tricks that all relate to training convolutional neural networks. So first, we'll talk about backpropagation, and what you'll see is that backpropagation is very similar to what we learned in the last unit. The differences here, we're focusing particularly on CNNs and deep networks. So as you can see, we're going to have L different layers. So this ... means there's an arbitrary number in this network, but a total number of L. And each of the layers has essentially the same form. You have activations from the previous layer coming together with weights and biases. In this case, these are convolutional weights, convolutional weight tensor. And the linear layer produces scores. Maybe we'll talk about these scores here. And then these scores go through an activation function, possibly also things like pooling to get the new activations. So keep in mind that these are going to be tensors. We're going to think of them in terms of the PyTorch conventions. So W is a 4-way tensor, X is a 4-way tensor, B is a weight vector, and of course we have different tensors and different feature maps for every layer, little l ranging from 1 to big L. If we have dense layers, we can also work in this framework because we know that dense layers are a special case of convolutional layers with kernel size 1 by 1 and feature maps of one vertical and one horizontal pixel. So convolutional kernels are, they can basically handle dense layers as a special case. Okay, so the forward pass, because each of our layers has this structure, we want that the very first one, that will be A0, we want that to be X. So that's just going to be how we initialize it. A0 is X. But then for any layer, starting from the first to the Lth, capital Lth, this is our convolutional, this is the linear stage, convolution. And then once we get the scores from the linear stage, we put them through our activation function. Then we put them through a subsampling pooling operation. We already talked about these details, so I won't really repeat them. The activation functions work the same as in the last unit. They just is a nonlinear function that works independently on each one of these coordinates. Each one of these tuples. But this subsampling pooling layer is new. So remember that the effect of pooling can depend on the data itself. So if we do max pooling, we don't know how to do the max pooling without actually looking at the data to see where the max is. So as a result of that, we're putting all the indices into this pooling operation: the batch, the output channel, the output pixels, as well as the input pixels. So when we have all this flexibility, we can basically represent any kind of pooling operation that could have happened. Okay, so we go through this pair of things for little L1 to big L, and then finally we're at the end of our network. We have the final scores, Z for the capital Lth layer, and those go into our cost. This is the non-script J that depends on particular batch I, and then we sum over our batch index I, and we sum over our batch indices to get the final cost. And this notation here, the boldface Z, we're thinking about this as a rank 3 tensor where it has a channel and pixels, and then the I here is the batch index. Okay, so this quantity is just a shorthand notation for that. Okay, so that's basically the forward pass. We start with this stuff and we move all the way through, computing all those quantities until we get our cost. Then, as we know, the backward pass starts at the right and goes left. Okay, so the first thing we have to do in the backward pass is we have to do the derivative of the final cost with the final scores. So that's dj dzl. And of course, this is a four-way tensor. And when we do our calculus, we want to do calculus with respect to just scalars. So I'm going to have to look at one particular element in that four-way tensor. So I'm going to look at the element that corresponds to batch index I, output channel M, and output pixel pair J1, J2. So I'm doing dj dz, and this is the script J that is a sum over the different batch indices I. And so basically there's only one I that I care about. All the other terms in that sum we can ignore. And so I can then focus on the ith term in that sum, which is this guy. Now, simplifying this further requires knowing exactly what cost we're using, like whether we're using quadratic or cross entropy or whatever. But we've seen all the usual examples of that derivative in the end of the Unit 8 packet, and so we won't go into more details right now. Okay, so the next thing we have to do now for backpropagation, we have dj dzl. So if I want to do dj dbl, then I do dj dzl times dzl dbl. And again here, I'm going to look at a particular entry, the mth entry in this, and then the usual question we have to ask is, how many different nodes does that affect here, because when we do the multivariable chain rule, we need to sum over all the affected nodes. So when you look at this, if we're talking about a particular M here, you can see that is going to affect all the batch elements I, as well as all the output pixels J1 and J2. So let's see, where did we end up? Yep, so this is where we were. So DJ, DBLM, we have to do the multivariable chain rule where we sum over all the batch indices and all the output pixels. Other than that, the calculus is pretty easy back from here. So DZL, DBLM is just going to be 1. So that's 1. So, and then this thing is what we already computed and stored as a number. So with that, we're done with DJ, DBLM. And we do that, of course, for each of the different M's. Next is DJ, DWL. So we're going to do DJ, DWL is DJ, DZL times DZL, DWL. And DJ, DZL we already computed, so we only have to worry about computing DZL, DWL here. And here again, we have to look at a particular element in this four-way tensor and ask the question, which variables here did it affect? So when we're looking at a particular element, so MN, K1, K2, you can see that this is going to affect only a single M corresponding to this M, but it's going to affect all the batch elements, all the different I's, as well as all the different output pixels J1 and J2. So when we do this multivariate chain rule here, we have the sum over I, J1, and J2. This we already computed, and this is pretty straightforward. DZL, DWL. Let's go back to this equation here. So DZL, DWL, you can see it's just going to be this number there. So this, you can see, is exactly what's down here. Okay, and so that's essentially we would then compute this for all combinations of M, N, K1, and K2. One interesting thing about how computationally intensive this is to compute is, as you can see, this is really just another correlation. So if we have hardware that is good at computing convolutions, things like GPUs that I'll talk about later, doing the forward pass, the sort of computations you want to be fast at in the forward pass are the same as the computations you want to be fast at in the backward pass. So, so there's a nice symmetry to it. Okay, so continuing with the backward pass, the next thing is DJ dA, L minus 1. So for that we have DJ DZL times DZL dA L minus 1. DJ DZL, we already computed that. Again, let's imagine if I have a single element of this four-way tensor, which elements here did it affect? So we have to come back to our equation here. And in this case, it helps to rewrite things a little bit because this is a little bit inconvenient. So this is what we're going to do. We're going to define this as, I'll write it as K1 prime. And we're going to define this as K2 prime. And so this means that K1 prime is J1 plus K1, which means that K1 is K1 prime minus J1. So, in other words, this is going to be k1 prime minus j1. This is going to be k2 prime minus j2. And so now we have a slightly different version of this equation where this refers to, I, n, k1 prime, k2 prime, and this w has some differences in those positions. And so that when we want to do dzl, dal, and we want to target exactly, one particular set of coefficients in al, it's easy to do that derivative. It's just this w here. So that is what we're doing over here. We're doing dzl, dal minus 1. And here's our weight matrix, and here you can see these are the differences. So on the previous page, I had called them k1 prime, k2 prime, so there's primes there. But on this page, I'm just replacing all the removing all the primes, and then obviously the expression still holds. Okay, so that's the explanation for where that came from. And once again, when you look at this operation, this is a convolution operation, which is very similar to correlation. It just has this flipping. So if we have hardware that's good for correlations, it's going to be good for convolutions, and we can do this quickly as well. All right, so that's dj dal, and then the next thing is dj dzl minus 1 here, which we can do dj dal minus 1 times dal minus 1 dzl minus 1. So this first term we computed above, that's done. And the next one is dal minus 1 dzl minus 1. This is not too difficult. That is from this equation here. So when we do d this divided by d this, we just have to differentiate this. We basically put a prime on that h, and then we multiply it by that. So that is how we got this. Here's our prime, our derivative on the activation function. So that actually takes us back. We computed basically all these guys here, and I think we also computed basically all the things in the backward pass. So as you can see, it's pretty similar to the case of the multi-layer perceptrons, except the main difference is, number one, there's more layers, and number two, they're convolutional. So instead of matrices, we have four-way tensors. All right. So we've been talking a little bit about, speeding up computation. So when they first were implementing these things like 10 years ago and before that, they had to use CPUs. CPUs are not really super great at doing lots and lots of convolutions. Modern CPUs can definitely do convolutions at a pretty fast rate, but when you have millions of parameters and millions of training samples, the number of convolutions you have to do to train a network is incredible. So you want to try to speed that up. So at some point about 10 years ago, someone realized that a lot of the processing operations that are being done in GPUs for graphical rendering are not so different from the sorts of things you want to do when you train these deep networks. So they said, I bet we can repurpose these GPUs for deep learning. And now there's a huge market segment of companies like NVIDIA that are selling a lot of GPUs that are very specifically for deep learning. And in fact, they're essential to deep learning. If you really have a big model and big data set, if you don't have one or more GPUs, it takes forever to train. Even if you have many, many GPUs with some of the really big models that they have nowadays, that things that like Amazon and Google are running, these things, even with hundreds of GPUs might take them months. So, things are just really have exploded. The chart here on the right shows an example of how much time it takes to process something. So this is if we have a single GPU. Here it's taking 180 seconds to do something. I'm not exactly sure what. But if you have two GPUs, you get a speed up of essentially, you can run it half the time. If you have 4 GPUs, you get another factor speed up by 2. But once you get to 6 GPUs, now it's a little bit harder to get the GPUs working together super efficiently. And so the reduction in compute time, you do get a little bit of a reduction, but it's not like a massive one. So, so there is a certain point where when you have many, many GPUs, the efficiency starts to tail off. But at first, it's pretty linear. And the blue line shows efficiency of a single GPU relative, or speed up, a single GPU relative to a CPU. So in this case, a single GPU is about 30 times as fast as one CPU, or 4 GPUs is 130 times as fast as one CPU. So there's definitely a whole range of GPUs with different amounts of memory and different processing capabilities. You can buy a workstation with a really nice GPU for deep learning for roughly $3,000. Maybe with supply chain issues and so on and inflation, maybe it's gone up a bit. Maybe, and of course it really depends exactly what GPU you want to get in it. Similarly, if you want to buy a server, a cluster that has many high-performance GPUs, I'd say it's going to cost at least $30K. Again, depending on how much memory you want to get and all that stuff, maybe even $50K to have 4 really state-of-the-art GPUs in it. Another option, if you don't want to spend all that much money up front, but you still want to do a little bit of GPU processing, is you can rent them. Google Colab is one famous source. They give you a certain amount of free credits. At some point, they want you to pay. It's not that expensive. Maybe like $1 for 1 hour of processing time. There's many other services beyond Google. If you click on that link, it'll take you to an article that lists many other options. But if some of you guys want to use these for your project and you don't have yourself a computer with a nice GPU in it, you might check out some of these services to speed up your training. All right, so let's talk about learning rate scheduling. So this is something we talked about briefly before, but the idea is, let's first talk about what happens if you just have a fixed learning rate. So we're not changing or scheduling the learning rate as we train. We just have a fixed one. So back in Unit 6, we were focusing on convex optimization. And essentially what we saw there is that if you have a learning rate that's too small, the only problem that causes is that it hurts in speed. In other words, it just takes longer for you to train your model, but your model will eventually get there if you give it enough time. So there's no real penalty in terms of accuracy if you can train it for longer. But it ends up being different with convolutional neural networks because these are non-convex. That when we train these, we have a non-convex optimization problem, and these problems can have bad local minima. This is just a very simple illustration in one dimension where we're trying to adjust the parameter x, and you can see we have a local minima here and here and a global minima here. And so the idea is if we initialize here and we go in the downhill direction with a very small learning rate, what's going to happen is we're going to converge here and we're going to stop there. Or if I started here with a small learning rate, I would converge here and I would stop there. But what we really want to do is we want to get here. So there's different things we can do to try to get there. One of the most common things to do is to use a large learning rate, which has the effect, if you have a shallow bad local minima, you can jump out of it. So maybe you take big steps and end up bouncing out and down here. And remember, this is stochastic gradient descent, so our steps are always, a bit random, a bit in the wrong direction, and that can actually be good when you want to jump out of a local minima. Now, if you use a large learning rate all the time and you never change it, what happens is you'll get down to the bottom and you'll just bounce around and you'll never really settle in the bottom. You'll just keep bouncing around. So the idea then is to use a large learning rate initially, but later in your training, use a small learning rate so that once you're in that good local minima or global minima, that you really can settle near the bottom. So that's the idea behind a lot of variable learning rate or learning rate scheduling schemes is first use a large one and then later a small one. Now, there's other approaches too. There's something called momentum, which means essentially rather than just following the steepest downhill direction, you have some momentum so that if you have some good momentum and you're in a shallow minima, you tend to, just with momentum alone, kind of keep going and fall out maybe into a better local minima here. So Adam definitely uses momentum and other tricks in its algorithm. There are many different learning rate schedules. So we talked about the simplest one is to start with a large learning rate and make it smaller. But there's the question is how quickly do you make it smaller? There's ones that are multiplicative, exponential, ones that go in steps. There's cosine learning rates that go up and down and up and down. Other forms of cyclic learning rate. And one that's shown to work particularly well is this so-called one-cycle learning rate, where you start here at, let's say, maybe a medium learning rate. You ramp it up over a number of iterations to a high learning rate. Hopefully you bounce out of all the bad local minima, and then you gradually decrease it back to the initial value, and then there's one last stage where you make it really small and you really try to settle down wherever you found. And if you carefully choose these two learning rates here, and you can do that with what's called a learning rate range test, then this is a very fast way to converge to a good local minima. Here's another picture. This is related to that learning rate range test here. And this shows after a fixed number of initial iterations what the loss is as a function of the learning rate you used. So if you use really small learning rates, you can see the loss doesn't really change very much. But then there's a range of good learning rates where the loss sort of grows down linearly with the learning rate. That's where we want to be in. Now, once the learning rate starts to get too big, then you can see the loss is kind of invariant to it. It's a good loss, but you can see it's a little bit inconsistent. And then once you make your loss really big, then the algorithm diverges and it just doesn't really work well. So this is sort of the range you'd like to be in, where things are going to work the best. All right, batch normalization. This is another trick that is very helpful to speed up training. And mainly this is something you want to use in dense layers. If you have, well, I take that back. The discussion on this page is what you would do with a dense layer. And then there's, actually no, I take that back again, sorry. So there's a couple different articles. One is specific to CNNs and one's not, just in these two links. Okay, so how does batch normalization work? So if we remember the process of standardization, we saw that there's a lot of benefits to standardizing raw features. And remember, standardizing is to make the means 0 and the variance 1. And this is something we typically do to our original data, right, our training data. One of the reasons why that's important in deep networks is because this particular variance is sort of how the designers of PyTorch and TensorFlow have assumed that you're going to pre-process your data. And they have chosen random weights with a distribution that works well with mean 0 and that variance. And if you initialize with a variance that's much bigger or much smaller than this, you're much more likely to get stuck in a bad local minimum. So this is, especially with neural networks, really important to standardize your data going into the network, or at least normalize it somehow, so that it's in the proper range. The idea behind batch norm is actually to sort of redo this process in each channel and in each layer. And when you do that in each channel and each layer, then the weights, the W's and the B's, are kind of well calibrated to the size of the inputs. So this is how we do it. So that's sort of the first part of it. So this equation shows for the Lth layer and the mth channel, this is how you would compute the sample mean. So the sample mean you're going to average over the batch and all the horizontal and vertical pixels. This is going to give you a channel and layer and channel specific sample mean. You can then subtract that sample mean from your features here and look at the average squared difference, and that's the variance, and then take the square root of the variance to get the sample standard deviation. Now, to prevent this number from going to 0, it's common to add a very small number here. And the reason why we don't want this to go to 0 is that this is the standardization process. You take your data, subtract the sample mean, divide by the sample standard deviation to try to get this to 1. And so if somehow during training this goes all the way to 0, you can see that this will go to infinity. You definitely don't want that to happen. Okay, so if we do this here, then the z's after this normalization will have 0 mean and unit variance. Now batch norm goes one step further, and it says, well, maybe 0 mean and unit variance isn't the very best combination. Maybe I can actually learn something that's even better for my task and for that channel and that layer. And so those learnable parameters are this gamma. Gamma LM will scale it. So if gamma LM is 1, the variance will be 1. But if gamma LM is greater than 1, the variance is greater than 1. And then here's your shift. That's basically your learned mean. So you do this standardization, then you do the rescaling, and finally you get this output z hat, which is what's going to come out of that channel and that layer. Okay, let's see some of the results of this. So this is an experiment from the original paper. This is for the inception network, which we'll talk about a little bit later. And this is over the number of training iterations, not epochs. So here we have 30 million. And this is just the reference trace that has no batch norm, just the network without batch norm. all these diamonds are at the same height. It looks like these are higher, but that's just an optical illusion. These are all the same height, so that's the same level of this is accuracy. So this is like 75% accurate, I believe. Okay, so once we turn on batch norm, you can see we get much faster convergence. That's this red dashed line, and in fact, we can get a little bit increase in terms of accuracy over the original network. Now, another thing that batch norm allows us to do is, because everything is much better conditioned throughout the network, it's possible to raise the step size significantly without causing any convergence issues. So if we multiply the step size by 5, we get this blue dotted line. Now you can see it's really converging quickly. But you can go further. You can increase the step size by a factor of 30. And then you get this solid blue line, and you can see not only is that converging quickly, but there's a sizable increase in performance that you can get over these other choices. And then they did one other thing that is kind of crazy. So if you remember, in deep networks, we have the vanishing gradient problem. If you use sigmoid or TANH activations, that can be really a problem because your gradients during backpropagation, they vanish, and you never get gradients in your early layers. So that's why we would typically use a ReLU in a deep network. But they said, if we use batch norm, we can even get away with using sigmoids. It's not the best choice, but you can see they still kind of work. So with sigmoids, you can get almost 70% accuracy. It's still not as good as these other techniques, but the fact that it works at all with batch norm is interesting. Okay, so when the first paper came out, it was there wasn't really a very good theory for why batch norm helps. It kind of makes intuitive sense that it might be a good thing to do, basically apply normalization at every layer and every channel. But there wasn't really that much theoretical analysis. Later, there were theoretical analyses of it, and there's various things you can say about it, about why it works. So some of these are kind of intuitive, some maybe less intuitive, but you can show with enough analysis. So basically, batch norm reduces variation across channels and across mini batches. So all the different channels behave similarly, and different over mini batches, things behave similarly. So that kind of uniformity allows you to do things like increase your learning rate because you're not worried about the worst case being so much stronger than the average that if you increase the learning rate, that worst case will explode. Another thing that it helps to do is it helps to decouple layers, make them work more independently of each other. And you can show that it actually makes this cost function smoother, and that's another way to understand batch norm. So there's all sorts of ways to understand it, but it works super well, and it's still something that is used today. Okay, so another very different technique that's interesting is called dropout. So dropout, the main purpose of dropout, you could say, is to reduce overfitting during training. So what you do is you temporarily remove a random subset of neurons in each mini batch. So here's an example where maybe these are the inputs, and then what you have after the first layer, what you have after the second layer, and finally the output, the loss. And we know the processing is where we see the arrows. That's the processing between layers. So on the left, a standard neural net, you're going to use all these variables, all the inputs, all the first layers, and so on. What you do during dropout is you randomly remove different subsets at each iteration. So at one iteration, you just drop out. You just basically don't use these values at all. You pretend they're not there. And then at the next iteration, maybe you include those, but you drop out some other ones. and so on. And so in some sense, it's kind of like giving your network a real workout while it's training. You're really making life hard for it, so it really struggles to be a lot stronger. It basically struggles in a good way. So that's what you do during training, but then during inference or testing, you put all the nodes back, and now they work very well together. They in fact can even work well, maybe relatively well over subsets, but when you put them all together, now they can work really well together. And one way to understand this is it's sort of like you can think of maybe this random instance as one version of the network, and then at another time you have another version of the network, and when you put them all together, it's kind of like you have a whole collection of subnetworks working together. So we call this an ensemble of simpler networks, and we're going to talk a lot about ensemble methods in the next unit 10. So we'll come back to this. But an ensemble is basically when you just have a collection of simple models that on their own might not work that well, but when you put them all together, they work really well as a whole. Okay, so that's basically what you do with Dropout. Just a few more details about the implementation. So we can think about it like this. So for every activation, so here we have an activation at layer L, batch index I, and output channel M. We're going to multiply. So there's still this is a whole image with many pixels. Actually, I take this back. So this is really being this discussion is for dense layers. Dropout is not very often used for convolutional layers, so it's mainly a thing for dense layers. So in the case of a dense layer, we don't have any pixels, right? We just have these channels, layers, and batch items. Okay, so this scalar, what you're going to do is you're going to multiply that by a Bernoulli random variable. That's a random variable that's either 0 or non-zero. And so, of course, when you multiply it by 0, it removes it from the network. And when it's non-zero, rather than multiplying it by 1, you're actually going to multiply it by 1 over p, where p is the probability that you don't turn it off. So, so the idea is the following. If you didn't do this scaling, and let's say you removed every node with a probability of 50%. If you do that, then the average value of that neuron would be 1/2, right? Because half the time it would be 0, half the time it would be 1. So by scaling this by 1 over that probability, basically it's making it stronger when it's non-zero. It preserves the average value. So as another example, if p is 0.1, then you'd either scale it by 0 or 10. So then on average, it's still 1. Okay, so again, importantly, this is something we only do during training. During testing, we use the full network. So here's a few things to note. So again, the whole purpose is reducing overfitting. And so if this network is too powerful, maybe these random subnetworks are closer to the capacity or power that you want. So when you use Dropout, it does tend to increase the number of training epochs. It does tend to reduce the capacity of your network. So if your network is not really overfitting that much, Dropout might not be helpful. However, if you still want to use it, what you could do is you could maybe add more channels or hidden nodes to your network to make it more powerful so that it is overfitting, and then reduce some of that overfitting with Dropout, and then get the benefit of an ensemble. So, and like I mentioned, for convolutional layers, there are other versions of Dropout, although I haven't seen them used very much. Okay, so we'll see we'll see an experiment with dropout in a couple slides. One last trick that is used quite a bit is called data augmentation. And this is just sort of an artificial way of increasing the size of a data set. So it's almost always the case that you wish you had more data than you do have. Sometimes you know about certain symmetries in the data set. So for example, if we're dealing with images, you might know that you could flip the image and it still looks, more or less like the same kind of image. Maybe you could shift it horizontally and vertically. Maybe you could scale it, make it a little brighter or darker. Maybe you could rotate a little bit. Maybe you could crop it a little bit. So this is just one example where we have one image, and by just zooming in and cropping it in a couple different ways, we've turned that single image into 3 images that all look a little bit different. So, so this is something, if you know about your data, you can do this. If you don't really understand the structure in your data, it's not really possible to do this. But when you work with images, you often know these things. When you do this, it's performed by the data loader in PyTorch, and there's a nice tutorial here. Okay. Another thing we can talk about briefly is improvements on ReLU activation. So when we first talked about ReLU, as we said, it's really good at preventing vanishing gradients. That's what you get if you have a deep network and you use sigmoid or hyperbolic tangent. And ReLU is nice because the gradient is 1 here and never less than 1. So when you cascade many of these as many stages of a network, any gradients that pass through the positive part are not diminished in size. However, sometimes what can happen is that after you're done training, you notice that a subset of nodes in your network are just doing nothing. They're always stuck outputting 0. So this is called the dead ReLU problem. And so one of the ways to avoid this is you give the slope, the left side, a little bit of a slope. So for example, this is called leaky ReLU. You might use a slope of 0.01. So overall, it still behaves the same, but this 0.01 is just enough to prevent these guys from getting completely dead and causes the network to learn to do something with those nodes. Now you can go even further and you can make what's called a parametric ReLU, where the negative side has a positive slope A that is learned. So rather than just assuming that you're going to use 0.01, you can initialize it at 0.01, but then see if you can learn a better choice of that slope. And there's many other choices of activations. Another one that is pretty popular is the exponential linear unit, or ELU. And so this one, for the positive side, it's just like a ReLU, so it's just a slope of 1. For the negative side, it is smooth. So if you look at this picture here, you can see that it's smooth here. It's non-zero over here, but it's not perfectly flat, but it gets very close to flat because as z goes negative, this becomes extremely tiny. And so this converges to minus alpha here. So this would be a case where alpha is 1. Okay, so this smoothness can often help the optimization algorithms, and so often this works pretty well as well. Okay, so just one last thing to talk about for this lecture then is a PyTorch demo in this unit. And there's several demos in this unit. This is demo B. So we're going to build a small convolutional neural network. It has 2 convolutional layers with ReLU and max pooling, followed by 2 dense layers. And we're going to use it to classify CIFAR10. So that's what I showed you way in the beginning of this unit. There's 10 classes of 32 by 32 color images. And so on the left, we have our training accuracy. On the right, we have our validation or test accuracy. And you can see that we're running for 100 epochs. And let's look at the baseline, the blue one first. So this is pretty common in neural networks for the training accuracy to approach 100%. But the test accuracy here is settling out at about 65. So, big difference between training accuracy and test accuracy. I really want to emphasize that the training accuracy is not that important in terms of the final, when you say how well is this thing working, just because you're getting 100% training accuracy does not mean that you have a fantastic network. If the network is powerful enough, it can essentially memorize the training samples. It doesn't mean it's going to do well on test samples, and that's what we see here. The validation or the test accuracy, that is what really matters at the end of the day. This is the number. Okay, so how can we improve this? Let's try adding batch norm. So when we add batch norm, you can see that the training slowed down just a tiny bit. So I think often it improves. It speeds up. So the fact that it slowed down a little bit maybe is a little surprising. But what's more important here is you can see that it gained about 5% in accuracy. What about dropout? Let's add dropout. So when we add dropout, you can see there's a huge effect on the training accuracy. The training accuracy drops by about 20%. But again, we don't really worry too much about training accuracy. And we expect that the training accuracy drops out because when we use dropout, we're removing, I think in this case, half of the nodes of the network. So we're giving it a really hard time during training. But then during validation or testing, you can see that we get a big improvement over batch norm alone. It's almost up to 80% now. And when you use dropout, it's not unusual for your test accuracy to be higher than your training accuracy. And this is because when you're testing, you're using the full network without dropping any nodes, whereas here during training, you're at every iteration dropping out a random subset of nodes. So really, you're kind of measuring two different networks. Now, as a last thing, we could try adding data augmentation. And it's a little bit surprising, but somehow data augmentation is making our training accuracy a little bit worse. And it doesn't seem like it's helping our validation either. Maybe we could conclude that maybe we have enough data in this problem, or maybe we can conclude that the type of data augmentation wasn't maybe a great match to the data set. Maybe we were doing things that were more confusing than helpful. Usually you'll find that data augmentation helps performance, but for whatever reason in this particular demo, it didn't help us. All right, so I think that's enough for this lecture, and hoping to record maybe one other one before I see you guys on Friday. Have a good one.